Hello everyone, my name is Shandini, student of SVCE. In this video, I'll be talking about relations and functions. In the contents, we have introduction, definitions of relations and functions, properties of relations, types of relations, representing relations, operations on relations, functions as special relations, properties of functions, function operations, inverse functions, applications of relations and functions, conclusion. Starting with the introduction, relations and functions are fundamental concepts in discrete mathematics, underpinning the study of sets, logic, and the foundations of computer science. Understanding these concepts is crucial for mastering advanced mathematical concepts and solving complex problems. Definitions of relations and functions. Relations. A relation is a set of ordered pairs that describe the association between elements from two or more sets. Functions. A function is a special type of relation where each element is the domain and paired with exactly one element in the codomain. Notation. Relations are typically denoted using the symbol R, while functions are denoted with the symbol F. Examples, relations, equality relation on A equals to 1, 2, 3, R is equals to 1, 1, 2, 2, 2, 4, 3, 3, 3, 6, 4, 4, 6, 6. Divisibility relation on A is equals to 1, 2, 3, 4, 6. R is equals to 1, 1, 2, 2, 2, 4, 3, 3, 3, 6, 4, 4. 6, 6. Functions. Identity function. The identity function on set A, ID. ID of A is equals to A for all A belongs to A. Constant function. A function f from A to B where f of A is equals to C for some fixed C belongs to A for all A belongs to A. Properties of relations. Reflexivity, symmetry, transitivity. Reflexivity, a relation R on a set A is reflexive if every element in A is related to itself. This means that for all x in A, x Rx is true. Symmetry, a relation R on a set A is symmetric if whenever x Ry is true, then y Rx is also true. The relation goes both ways between any two elements. Transitivity, a relation R on a set A is transitive if whenever x r y and y r z are true, then x r z is also true. Then the relation can be chained across multiple elements. Combinations. Relations can exhibit various combinations of these properties, leading to different types of relations, such as equivalence relations and partial orders. Types of relations: equivalence, partial order, total order. Equivalence relations participation a set into disjoint subsets where elements within each subset are considered equivalent. They exhibit the properties of reflexivity, symmetry, and transitivity. Partial order relations. Partial order relations establish a hierarchical structure where some elements are related but not all. They satisfy the properties of reflexivity, antisymmetry, and transitivity. Total order relations. Total order relations impose a complete ordering on a set where every pair of elements is comparable. They exhibit the properties of reflexivity, antisymmetry, and transitivity. Representing relations. Relations in discrete mathematics can be visually represented using matrix notation or graph diagrams. Matrices provide a tabular format to capture the connections between elements, while diagrams illustrate the relationships more through nodes and arrows. These visual tools aid in analyzing the properties of a relation, such as reflexivity, symmetry, and transitivity. They also facilitate understanding the different types of relations, including equivalence, partial order, and total order. Matrix representation, a relation R on a finite set A is equals to A1, A2 to an can be represented by an n cross n matrix M, where M of ij is equals to 1 if ai comma aj belongs to R and M of ij is equals to 0 otherwise. Directed graph, a relation R on a set A can be represented as a directed graph where each element of A is a vertex and there is a directed edge from vertex A to vertex B if A comma B belongs to R. Operations on relations. Composition. Combining two relations by linking elements that are related in both relations allows exploring complex relationships between sets. Inverse, reversing the direction of a relation where the domain and codomain are swapped, useful for analyzing the reverse of a given relationship. Closure, finding the smallest superset of a relation that satisfies a given property, such as transitivity, expands the reach of a relation. Functions as special relations. Functions are a special type of relation where each element in the domain is paired with exactly one element in the codomain. They represent a unidirectional mapping between two sets, satisfying the property that no input is associated with more than one output. Functions are essential in many areas of mathematics and computer science as they provide a formal way to model relationships and transformations between different entities or quantities. Properties of functions: injective, surjective, bijective. Injective one-to-one, an injective function maps each element in the domain to a unique element in the codomain. No two elements in the domain are associated with the same element in the codomain. Surjective onto, a surjective function maps every element in the codomain to at least one element in the domain. There are no gaps in the codomain. Every possible output value is covered. Bijective one-to-one and onto. A bijective function is both injective and surjective. Each element in the domain is mapped to a unique element in the codomain, and every element in the codomain as a corresponding element in the domain. Properties of functions. Domain and codomain. The set A is the domain and B is the codomain of F. Image. The image of F is the set of all values f of A for A belongs to A denoted as Im of F. Function operations. There are two function operations which are composition and inverse. Inverse function is a function that undoes the effect of the original function. It reverses the relationship between the input and output. Finding the inverse. To find the inverse of a function, we swap the x and y variables and solve for y in terms of x. The inverse function is denoted as f to the power minus 1. Properties of inverse functions. Inverse functions are only defined for one-to-one functions. The domain of the inverse is the range of the original function and vice versa. Applications of relations and functions. Set theory applications. Relations and functions are fundamental in set theory, enabling the analysis of complex relationships between elements. They find applications in fields like computer science, logic, and mathematical modeling. Decision making. Functions describe how inputs map to outputs, making them useful for predictive modeling and decision support systems. Relation analysis can reveal dependencies and inform strategic choices. Database design. Relational databases leverage the mathematical concepts of relations to structure and query data effectively. Functions define how data entities are connected and transformed. Conclusion. Relations and functions are essential concepts in discrete mathematics, providing the foundation for understanding more complex structures and systems. Relations describe how elements of sets can be associated with each other, while functions specify precise mappings between sets with special types of properties enabling various applications across mathematics and computer science. Thank you.